Hello everyone, welcome to my channel Tip Tuition Class. So you all know that in previous video we have started the chapter 1 from CBSE NCERT match, isn't it? So in today's video I'll be starting the exercise 1.1 taking the help of the previous example. If you have not watched that video, I have given the link in the description below. Kindly watch it. Alright, so if you are new to my channel, please like, share and subscribe and hit the bell icon for more update. So let us start exercise 1.1. So the first question in exercise 1.1 is use Euclid division algorithm to find the HCF of number 1 135 and 225, number 2 196 and 38220, number 3 3867 and 225. Alright, so taking the help of the previous example, we are going to solve this problem. Alright, so I have given the link in the description below. Kindly watch that example, kindly watch that explanation properly. Alright, so that it will be easy for you all to solve this problem. Alright, so let us proceed to solve the question number 1. So student, this is our first question, right? Here we have to look which one is greater first. 225 is greater than 135, alright, or 135 is smaller than 225. So our divisor will be 135 and dividend will be 225. Remember, we have to follow the Euclid division algorithm. That was followed by Euclid division lemma, isn't it? So A equals to BQ plus R. This is the form which it has to satisfy this equation, and we have to get two such unique integers that is in the form of Q and R. Alright, so when you divide 135 into 1 is 135, so 5 minus 5 0 and 9 12 3 9. So this will become our divisor and the 135 will become our division. In such a manner we have solved the previous example, isn't it? So 90, 35, 91 is 90. So it is 5 and it is 45. So let us write for this. First of all, the first step was 225 equals to 135 into 1, 135 into 1, B into Q plus R was our 90. Isn't it? So our second step, 135 became our dividend and then 90 into 1 plus 45, isn't it? Similarly, now 45 will become our divisor and 90 will become our dividend. 45 2 is 90. Alright, so our 90 is here dividend A, B is our 45, Q is our 2 plus 0. So as I mentioned, in whichever step the remainder is 0, using that divisor, if you are getting the remainder 0, then that we will consider it as a HCF. So therefore HCF of 135 and 225 is equal to 45. Alright, so this is our first step. So A equals to BQ plus R. Alright, I hope you have understood. So student, this is our number 2 question, that is to find the HCF between 196 and 38220. So here we know that 196 is very less than 38220. So our 196 will become divisor, 38220 will become dividend. So if this is the condition, if two integer, if you are if you have two positive integer, then it should satisfy the condition A equals to BQ plus R, in which there will exist a two unique integer Q and R. Alright, so 196 196 is 6 8 1 2 will come here. So we have to do continuous division here, like we were doing in the lower section. That continuous division we used to do, isn't it? Because this is a bigger number, so within a one step only we have to get our answer. Alright, so is 9 is possible here, because 1764 is only the case, minus and 8, it is 9 here. Okay, 0 0 will come down, So 196 5 is 980. Alright, so within one step we got our answer. That is, our A is 38220 is equal to B is our 196. Our Q is 195 plus our remainder is 0. So as I have told you, within one step also you can get your answer. So using the divisor, this, if we are getting the remainder 0, then that is our answer, as I mentioned. Therefore HCF of 196 and 38220 is equal to 196, isn't it? So this is our answer. Alright, so this is a third question from exercise 1.1. So similarly we will try to solve 200 and this is 255. 255 is less than 867. Alright, so if such is the condition, then we have to, if you have the two positive integer A and B, if suppose this is our A and this is our B, A and this is our B, then it there exists a unique character in the form of B, Q and R, which satisfies the equation A equals to BQ plus R. Alright, so 867 became our dividend and 255 became our divisor. So 255 into 3 is possible. 3 is a 15, 1, 7. Alright, so 7 minus 5 is 2, 6 minus 6 is 0, 8 minus 6 7 is 1. So now 255 will become our dividend. So let me write first of all, A is our 867 is equal to B is our 255 into Q is our 3 times we are multiplying plus R is our 102, isn't it? So this is the condition. So similarly 102 into 2 is 2 2s are 4, 2 0s are 0, 2 1s are 2, 1 5, so 51. So 255 is equal to 102 into 2 plus 51 is the remainder. So now 51 will become our divisor, 102 will become our dividend. So 51 2s is 1 2, 5 2s are 10. So 102 is equal to 51 into 2 plus 0. So whichever using whichever divisor, if you are getting the remainder 0, as mentioned earlier, the answer is that, isn't it? So therefore HCF of 867 and 255 is 51. Alright, I hope you are clear with this. There is no doubt, right? So student, this is number 2 question from exercise 1.1. Alright, the questions is, so that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. Alright, so you have to prove that any positive odd integer. Okay. Alright, you know what is odd? Odd number are those number which are not divisible by 2. Not divisible by 2, isn't it? So in the 6 table, so 6 1 is 6, 6 2 is 12, 6 3 is 18, 6 4 is 24. So these are all the even number. So we have to get that integer odd. We have to show any positive odd integer which will be in the form of 6q plus 1. Alright, so you will understand what is this. Okay, so let us solve the problem. Solution. So here we have to do like this. Let A be any positive integer and B will be equals to 6. Why? Because 6q plus 1, this is our, if this is our A equals to 6q plus 1, then A is our A. We have let that A be any positive integer and B should be our 6, no? So A is our A and B is our 6, right? So B is equal to 6. Alright, we have laid that. Now using by Euclid division algorithm, we know that A equals to BQ plus R, isn't it? A equals to BQ plus R, where R should be greater than or equal to 0 but less than or equal to B, isn't it? So what are the possible values for R? We can calculate this, we can recognize it, isn't it? Possible values of R will be starting from, possible values of R will be 0, 1, 2, 3, 4, 5. Now why? So why it is until 5? Because according to this statement, R should be equal to, R should be less than B or equal to B. Alright, so let us assume only less than B. That means it will start from, what is the value of B? The value of B is 6. The value of B is 6. So the possible values will be 0, starting from 0, right? 1, 2, 3, 4, 5. Alright, let us assume till that. Okay? Okay. So if when R is equal to 0, then what should be our condition? A is equal to 6Q plus, in place of R, if you put this 0. Alright, if you put this 0, then it is a 6Q. Then this is a even, no? If Q be any integer, suppose say 1, then 6 into 1 is equal to 6, multiplication. If suppose Q is our 2, then 6 into 2 is equal to 12. If 6 is our 3, then Q is our 3, then 6 into 3 is 18. So this becomes our even. So when our R is equal to 0, then the value of A is equal to 6Q. So that will become our even, isn't it? So when our R is equal to 1, then A is equal to 6Q plus 1. In place of R, A is equal to BQ plus R. In place of R, it is 1. So then we can write, if suppose say Q is equal to 1 plus 1. 616 plus 1 is equal to 7. So yes, this is our odd. For every condition, say, suppose if you have 6 into 2, if in place of 2, if you have 2, if in place of, 6 into Q, if suppose your Q is 2, then 6 to the 12 plus 1 is equal to 13. So this is also our odd number, which is not divisible by 2. Odd, isn't it? So this is odd, we can say, when our R is equal to 2 till 5, we have to prove it like this. A is equal to 6Q plus 2. This should be our even. Why? Because 6 ones is 1 plus 2. The 6 ones are 6. 6 plus 2 is 8. So we will get even for this. Alright. So we have to prove for 6Q plus 1. We have got this. Now we have to get for 6Q plus 3. So R is equal to 3. Therefore A is equal to 6Q plus 3. This is our odd. You can try. How? Just see. 6 if in place of Q you have 1 plus 3. 6 ones is 6 plus 3 is equal to 9. It is not divisible by 2, is it? That is odd, right? So similarly, if your R is equal to 4, then A is equal to 6Q plus 4. This is our even number. You can try. How? 6 into 1 plus 4 is equal to 6 1 is 6. 6 plus 4 is our 10. So it is divisible by 2, that is 5. So this is our even. So our next condition, last condition is 5. Therefore A is equal to 6Q plus 5. 6 1 is 6. 6 plus 5, 11. That is our odd. isn't it? So this thing we have to prove, that is we have to prove. So with this, what we can write, so what we have to prove, we have to prove that 6q plus 1 for any positive odd integer, 6q plus 1, 6q plus 3, 6q plus 5 is a odd, isn't it? So we have proved that therefore we can write for any positive odd integer is in the form of what? 6q plus 1, we got this. For any positive odd, our q was some integer, and that q was our integer. That using that integer, if you are getting odd, then that statement was, that positive odd integer was shown, okay, proved. So in the form of 6q plus 1, 6q plus 3, and 6q plus 5. Alright, I hope you have understood. We have to solve in such a manner using Euclid division algorithm. Let me brush up this again. Let me revise this once again. So we had to prove that any positive odd integer is of the form 6q plus 1, 6q plus 3, 6q plus 5. Alright, so odd means which is not divisible by 2. Alright, which should not be divisible by 2, like 11, 12, 13, 15 are the example of odd number. So using the concept of your Euclid division algorithm, what I have done is, let a be any positive integer and b is equal to 6. So we can write from here. Alright, we can write b is equal to 6. So using Euclid division algorithm, what it was given that when you have two positive integer, there exists a unique integer, that is q and r, so which should satisfy the condition a equals to bq plus r, where r should be greater than or equal to 0, or it should be less than, but it should be less than b, isn't it? So we can write the possible values of r from here, right? So what is the value of b? 6, right? The value of b is 6. So the possible values of r we can write starting from 0, 1, 2, 3, 4, 5. It should be less than 5. It should be less than 6. Till 5 we can write. Alright. So when our r is equal to 0, we can write a equals to 6q plus 0. Right. So a is equal to 6q. This is even. When you put any positive integer, in case of q, say 1, 2, 3, the 6, 1, the 6, 6 to the 12, 6 to the, you know the division, no? In every form, every multiplication of the 6, you'll get even number. Alright, so we'll get even. So this is our first case. Second one is when your r is equal to 1, a is equal to 6q plus 1. This is our odd, so we can multiply and get the value also, whether it is odd or even. So like this we have solved, and therefore for any positive odd integer is in the form of 6q plus 1, 6q plus 3, and 6q plus 5. This is proved. Okay, one thing we have to write here is a equals to b is 6 here and q plus r. Alright, we have to mention that also. Okay, so I hope you are clear with this. Alright, so let us proceed to the next question. So student, this is our number 3 question. The question states that an army contingent of 616 members is to march behind an army band of 32 members in a parade. Alright, the two groups are to march in the same groups of columns. The two groups are to march in the same numbers of columns. Now you have to find what is the maximum number of columns in which they can march. So 616 members is marching behind an army band of 32 members in a parade. What you have to find is, you have to find the maximum number, कितना ज़्यादा number of columns हो सकते हैं उनमें in which they can march. So to solve this type of a problem, you have to find the HCF. So using the Euclid division lemma, Euclid division algorithm method, we are trying to solve the method. Okay, here the question is, so what are the two positive integers? So these are the two positive integers, 616 members and 32 members in a parade. Alright, so using that numbers, we will try to find the maximum number. That is, maximum is HCF, highest common factor, right? So maximum number of columns in which they can march. All right. So while I'm solving the problem, I'll not be showing the questions. All right. You have to keep your book with yourself to see this, to see the problem. All right. So student, this was our overall question, right? We have to find the maximum number of columns in which they can march using the number 616 and 32. So using the Euclid division method, when you have two positive integer a and b, it should possess some unique integer in the form of q and r, which should satisfy the condition a equals to bq plus r, isn't it? This is my r. Alright. So when my a is 616 and b is 32, and let me write this. This is our using by Euclid division method. Okay, Euclid division method. So 32, when you divide 616 by 32, you'll get 32. Let us write 32 ones are 32. If you know the multiplication, you can write direct also. Okay, so 296. So 32 9 is possible here. So 209 is 18, 9 28. Okay, now next is 8 is our remainder, other are 0. So what is the case? So here what we have to do is 32 will become our divisor. Alright, see that this 32 will become our divisor, and dividend, and 8 4 is 32. Alright, so what we have done, 616 is equal to 32 into 19 plus 8, and then 32 will be equals to 8 into 4 plus 0. We can do this also. Alright, so if such is the condition, if this 8 becomes our remainder and nothing else, we have the other thing, then our first divisor will become our dividend. Alright, so 8 4 are 32. So this is the new case which we have solved. So HCF of 616 and 32 will be 8, because using this divisor we got the remainder 0. So therefore the maximum number of columns in which they can march, was equals to 8. Was 8. So to solve this type of a problem, we have to follow the concept of Euclid division. Alright, so I hope you are clear with this question. So another question from exercise 1.1 is question number 4, which state that using Euclid division lemma, use Euclid division lemma to show that the square of any positive integer is either in the form of 3m or 3m plus 1 for some integer m. Okay, what is the meaning of this? Chalo, let us understand. First of all, let us understand the question. The question is stating that अगर आप कोई भी एक पॉजिटिव इंटीजर लोगे, मान लो x, उसको अगर आप स्क्वायर करोगे, if you square that positive integer, then it should be in the form of वो 3m के फॉर्म में होना चाहिए, या फिर 3m plus 1 के फॉर्म में होना चाहिए, जहाँ पे m will be certain integer, some integer. Alright, so let us solve this problem also. So this was our question, right? So let us solve this. Let a be any positive integer here, and b is equal to 3. B is equal to 3 using this. So using as Euclid division lemma, we have to solve this, right? So what is Euclid division lemma? A equals to bq plus r. When you have two positive integers a and b, there should exist a two unique integers that in the form of q and r. Okay, where r should be greater than or equal to 0, but less than b, isn't it? This is the form. So using this method we are going to solve the problem. Okay, so if our a is our a, b is our 3q plus r, we can write in this form, because we have let a as a and let a be any positive integer and b be 3. Alright, so similarly we will try to solve this problem in which we have solved in question number 2. Okay, so possible values for r is equal to, if your b is equal to 3, then possible values will be 0, 1, 2. Alright, so we can write when r is 0, then a is equal to 3q plus 0, isn't it? So a is equal to 3q we can write. So if any integer, if you have, when you square this, it should be in the form of 3m or 3m plus 1. So let us square this. Squaring left hand side and RHS or both side. Squaring both side. Okay, so let us square. A square is equal to 3q whole square. So a square we can write is equal to 9q square. So next what we can do, a square is equal to 3, common we can take 3q square. Why I am doing this, you will understand it. Alright, so a square is equal to 3q square, we can write k1. What is this k1? I'll explain you later. Alright, you will understand what is this k1. Alright, so this way we have to solve. So another when r is equal to 1, then a equals to 3q plus 1. So a equals, now squaring both side again, squaring both side, we'll get a square is equal to 3q plus 1 square. So we can write a square is equal to this is in the form of a plus b whole square, so we can expand this, a square plus 2ab plus b square. So we can write a square is equal to 9q square plus 6q plus 1. Alright, so if such is the condition, then a square is equal to, from this 2 we can take 3 common, 3q square plus 2q plus 1. We can do this. So a square is equal to, let this 3q square plus 2q be k2 plus 1. Alright, k2 is our, this is our k2, this is our k1. So this is our second condition. Alright, so third, let us write here, when r is equal to 2, then what should be the condition? When r is equal to 2, then a is equal to 3q plus 2. So again we squaring both sides, squaring both side, what we are going to get, a square is equal to 3q plus 2 whole square is equal to, a square is equal to a plus b whole square, again a square plus 2 a b plus b square. Alright, so a square is equal to 9q square plus 2 3 is 6, 6 2 is 12, q plus 4. So over here what we can take the common, so let us do one thing here, 9q square plus 12q plus, we can write 3 plus 1, we can break this, 4 is equal to 3 plus 1. Alright, we can do this, so we have done this. So to take the common 3, I have done this. So 3q square plus 12, 4 q plus 1. We can take the common like this. So our next 3q square plus 4q plus 1 will be our k3 plus 1. Alright, so here, let me write here k1, k2, and k3 are some integers. So our some integer is m, right? So we can write for the first condition 3, k1 is our integer, some integer, so according to the question m is also integer. So in the second condition 3m plus 1, so we can write like this 3m plus m. Why? Because k1 is our some integer, k2 is our some integer, and k3 is also some integer, and according to the question our m is also some integer, so we can write k1, k2, k3 is equal to m. So therefore square of any positive integer is in the form of 3m, 3m plus 1. Alright, this is proved. I hope you have cleared, because using squaring both the side we have to solve this. So I have solved squaring both side, and I have let this 3q square k1 so that it will be easy for you to understand. Okay, over here I have done some trick. 4 I have breaked in 3 plus 1. So using that concept I have solved this problem. Alright, I hope you have clear with this. So let us move to the next question. So student, this is the last question, that is question number 5 from exercise 1.1. Alright, so let us solve this. So we have to solve using the Euclid division lemma to show that cube of any positive integer is of the form 9m, 9m plus m, 9m plus 1, and 9m plus 8. So here in the previous question we have dealt with the square, so here we are going to deal with the cube. Cube means in any of the variable the power should be 3, isn't it? Cube, that is cube, power of 3. So what I'm going to do here is let a be the positive integer, and b be 3. Alright, so I'm letting this thing. So we have to solve using Euclid division lemma. What is Euclid division lemma? When you have two positive integers a and b, there exist two unique integers that is in the form of q and r, which satisfies the equation a equals to bq plus r. So this is our Euclid division lemma. Alright, so this is what we have. So using this concept we have to solve this problem. Alright, so what they have said is what we have, let a be the positive integer and b be 3. So in case of b we can put here r like this. So if b is equal to 3, then the possible values of r is equal to what? R is equal to 0, 1, 2, as because r is greater than or equal to 0 but it is less than b. So if b is 3, then 0, 1, 2 should be the value, isn't it? So if such is the condition, then when r is equal to 0, then what should be the equation? A equals to 3q plus r. A is equal to 3q plus, if r is equal to 0, then put the value of 0 here, r here. A is equal to 3q. So they have asked us to show the cube of any positive integers, right? So what we are going to do, cubing both side. All right, a cube is equal to 3q cube. So after solving this, what will come? A cube is equal to 27q cube. So I'm here going to take the 9 common. 9 3 is 27. Okay, so our 3q cube here is an integer. So q is an integer, so m is also integer here, right? So I'm going to put here m. So a cube is equal to 9m. So this is the first condition. Similarly when r is equal to 1, then a is equal to 3q plus r. And what should be the condition? 3q plus 1 here. So again, what we are going to do here is cubing both side. Why? Because they have asked us to show that the cube of any positive integer should be in the form of 9m plus 1. That we have to provision it. So cubing both side, a cube is equal to 3q plus 1 whole cube. So what we can write, a cube is equal to, can you see this is in the form of a plus b whole cube? A here is 3q and b is equal to 1. So what is the formula of a plus b whole cube? Is a cube plus b cube plus thrice a square b plus thrice a b square. A cube plus b cube plus 3a square b plus 3ab square. Alright, so we are going to write in this form. So a cube is 3q cube plus b cube is 1 cube plus 3a square is 3q square into b is 1 plus 3a is 3q, b square 1 square. Alright, so this is a cube is equal to 27q cube plus 1 plus 3 3s are 9, 9 3s are 27 q square into 1 is 1, 27 plus 3 3s are 9 q into 1 is 9q, isn't it? So a cube is equal to, so let us shuffle this in a systematic form, that is from greater power to the lower power. 9 plus 27 q square plus 9q plus 1. So this should be in the form, so q cube is the highest power here, then after that is square, then no power, then nothing, 0 power. Alright, so over here it is 1 power. Okay, so a cube, what we can do, just see this condition till here, from not considering 1, you can take 9 common. 3 is 27 q cube plus 3q square plus 1 q or nothing else, just q plus 1 we can do. So this should be our integer, q cube plus q square plus q, we are considering one integer, that is m. Alright, so 9m plus 1. So this is our second condition. So let us try to prove third condition. So our next value of r is, when r is equal to 2, then a is equal to 3q plus r, then a is equal to 3q plus 2 should be the condition. So let us cubing both side, cubing both the side. A cube is equal to 3q plus 2 whole cube, isn't it? So I have told you the formula of a plus b whole cube, so we have to expand this into that form. So what is the formula? A cube plus thrice a square b plus thrice a b square plus, okay, a cube plus okay, I forgot to mention b cube, so we can write b cube here also, no problem. A cube plus b cube plus thrice a square b plus thrice ab square. Okay, so this is the form. You have actually a cube plus b cube plus thrice a square b plus thrice a b square, isn't it? But what I did is I forgot to mention that b cube, so I have kept over here. No problem is there. A cube is equal to 27 q cube plus 3 3s are 9, 9 3s are 27, 27 into 4, 54 q square plus 3 3s are 9 and 2 2s are 4, 4 36 q plus 2 2s are 4, 4 2s are 8. Alright, so it is already arranged in the sequential order of its power, so no need to arrange here. A cube is equal to, so another, what we have to do here is we will, okay, so here I'm going to take the common of this 3 side. Alright, so 9 3s are 27, 9 6 are 54, 9 4s are 36 plus 8. So this is, let's consider this is our integer, so 9m plus 8. Alright, so this we can do and we can write that like this. Alright, so you saw that we got this 3 form, that is 9m plus 1 or 9m plus 8. We got this 3 form after cubing any positive integers, so we can write therefore cube of any positive integer is of the form 9m plus 1 or 9m plus 8. Alright, so this is proved. Alright, so student, we are over with exercise 1.1. Alright, so in the next video I'll be starting another major important topic, that is fundamental theorem of arithmetic. Alright, thank you for watching video till the end. If you like the video, please like, share and subscribe and hit the bell icon for more update. Thank you everyone.